Is actually continues pretty smoothly. Practice point about the world as we want it, the world as it is. And first up, Lunjia will tell us about Omnipredictors for constraint users.
Thanks, Omer. Thanks, everyone. I'm Lunjia. I'm very glad to be here and talk about this joint work with Inbao, Omer, and Shutong on Omnipredictors for constraint optimization. Many talks in this workshop mention Omnipredictors, and indeed, Omniprediction is a very powerful notion that allows us to train a single model that can be easily adapted to minimize many different loss functions. And the goal of this talk is very simple. I'm going to show you that the idea of Omnipredictors can be applied to a much broader range of tasks and specifically to constraint optimization. And hopefully this will make the notion of Omnipredictors more applicable in practice. So if you are watching this video on YouTube, hit like, subscribe, and write nice comments. I really appreciate it.
Very good. Bravo. Do it.
So I start by giving an introduction to Omnipredictors. So Omnipredictors work in scenarios where we take actions to minimize loss. So just to set up the notation, I'm going to give you some very simple examples. So a graduate school needs to decide on whether to admit a student or not. So these are the decisions, these are the actions that the school can take. And in order to choose which action to take, let's suppose the school makes predictions about whether the student will be successful or not. And let's say in this case, there's a loss associated with failure to admit a successful student. Throughout the talk, I will use lowercase a to denote an action, and I will use capital A to denote a set of actions that we can choose from. And for the purpose of this talk, let's focus on binary outcomes denoted by Y. And the loss is a function of the action and the outcome and is a real number. It is a very simple setup, but it captures many examples. There's another example where the action corresponds to the number of loan we want to approve for a client. And in this case, we try to predict whether the loan will be repaid or not. And if we want to maximize our profit, then the loss is the negative profit. So in such loss minimization problems, if we know the distribution of the outcome, then it is very easy to find the best action to take that minimizes the expected loss. Here, the outcome is binary, so it follows a Bernoulli distribution with mean p. And if we know the value of p, then we can just easily find the optimal action. We just write down the expected loss, find the action that minimizes it. I will use KL to denote the optimal action to take. For many loss functions, there are closed form solutions to this optimal action. So indeed, KL is a function that is usually extremely easy to compute.
Unconstrained resources so that you can admit as many students as there are potentially successful students?
Yeah, so the question is, can we just, in the first example, admit everyone? So in this case, that's what you should do. But in practice, there are constraints. And the title of this talk is Omnipredictors for Constraint Optimization. So hold on. Yeah, so in practice, usually we're dealing with much more challenging scenarios. We don't know the distribution of the outcome, and we have to learn the distribution from data. And we want to automate the process so that we can efficiently assign actions to, say, thousands of individuals. So to model such more challenging scenarios, we assume that there's underlying distribution D over individuals and outcomes. And we collect data points from this distribution, draw an IID from this distribution, and we learn from these data points to get a model that can assign an action to each individual. And our goal is to minimize the expected loss over the distribution D. This loss minimization problem is standard in the machine learning literature. People have developed many different algorithms for minimizing various loss functions. And an easy observation here is that for different loss functions, the model you get from minimizing those loss functions are quite different. So it is obvious that if a learning algorithm wants to solve this loss minimization problem, it needs to know what the loss function is. And the idea of omniprediction is to do loss minimization without knowing the loss function. And how could that be possible? So the idea is that the loss is revealed after training time, but before the actions are taken. So let me explain this using a pipeline. In standard loss minimization, we have a learner which collects data and knows the loss function. It outputs a model, and the model can take actions, assign actions to individuals. In Omniprediction, we also have a learner which collects data, but the learner does not know the loss function. And after the learner produces a predictor, the loss is revealed to a post-processing procedure. And after that, the post-processing procedure assigns actions to individuals. So what makes Omniprediction powerful is that for different loss functions, we don't have to train different models. We can use the same exact fixed predictor. And the only thing that changes with the loss function is the post-processing procedure, which is supposed to be extremely simple and extremely efficient. So what this means is that Omniprediction allows us to adapt to different loss functions that may change over time, or loss functions that are unknown at training time. So indeed, Omniprediction is very powerful. So formally, we say a predictor is an omnipredictor if for any loss function L from a family of loss functions, the expected loss achieved by KL of P of X is upper bounded by the expected loss achieved by any hypothesis C in a hypothesis class, capital C, plus some small error epsilon. And here, this KL function plays the role of the post-processing procedure. And it is indeed extremely simple. As we defined at the beginning of the talk, KL is the optimal action to take if we pretend that the outcome Y follows the Bernoulli distribution with mean P of X. And as I said, usually KL is extremely easy to compute. And in this definition, the predictor P is fixed for all the different loss functions. And the only thing that changes with the loss function is the post-processing KL. It's exactly what we want. The idea of Omniprediction was introduced by Parakshit, Adam, Omer, Wetzel, and Udi, and this idea was further explored in a follow-up paper through the lens of outcome indistinguishability. So the main results of these papers is that Omnipredictors not only exist, but also they can be efficiently learned from data under very mild assumptions on the loss function. This is an informal statement of several theorems from these papers. There are many other different versions. The details are not very important. That's not the point. The point here is that we do have algorithms that can learn multi-calibrated predictors or multi-accurate predictors. Michael has told us that he gave us a lecture on such algorithms in his talk, for example. And indeed, some of these algorithms have been implemented in practice. So what this theorem tells us is that indeed, Omniprediction is practical. So if we try to apply Omniprediction to practice, we realize that many problems in practice are not just loss minimization. They also require constraint satisfaction. So for example, in the admission setting, we may have a budget constraint which limits the number of students we can admit. And we may also have a fairness constraints because some demographic groups have been historically discriminated, and we want to take affirmative actions to admit a fair number of students from those groups. And such constraints also apply to the loan application setting. So in these settings, you might find that the loss function doesn't quite change over time. They may change, they may not, but it is very natural for the constraints to change over time. We may have a different budget each year, and the fairness policy may change as we better and better understand how to protect disadvantaged groups. So in these scenarios, it would be extremely helpful if we could have an omnipredictor that allows us to adapt to the changing constraints so that we don't have to retrain a new model every time we have a new budget or every time the fairness policy changes. So and as I will show you in this talk, indeed, we show that we can construct Omnipredictors for such constrained optimization problems. So in other words, what we will do is to add constraints into this pipeline. Of course, here in Omniprediction, the learner knows neither the loss function nor the constraints, and they are revealed after training time and only to the post-processing procedure. And again, we want the post-processing to be extremely simple and efficient. The constraint optimization problems we consider in this talk will be of this general form. It has a objective function f0 and many constraint functions fj. I will come back to this formulation later, but here I will just mention that in our paper, we consider even more general versions of constraint problems where we combine different constraints and even different objectives using arbitrary Lipschitz functions, but that is beyond the scope of this talk. Any questions at this point? Cool. So the first thing we need to do in order to construct Omnipredictors for constraint problems is to define Omnipredictors for constrained problems. So to do that, let's take a closer look at the unconstrained definition, where we have this KL function that plays the role of the post-processing. And this KL function can be understood using this following optimization problem over a new distribution, dp, which we call the simulated distribution. The dp is defined after we obtained a predictor p. And dp is defined so that the marginal distribution of the individual x is the same as the marginal distribution of x from the true distribution d. But the distribution of the outcome y is the Bernoulli distribution with mean p of x. So what this says is that dp tries to simulate the true distribution by first drawing the individual x from the true distribution, but then it generates fake outcomes using the Bernoulli distribution with mean p of x. And almost by definition of KL and dp, you will realize that KL of p of x is the solution to the optimization problem on the simulated distribution. So what this says is that the post-processing procedure is equivalent to solving the problem on the simulated distribution. So in the unconstrained setting, we do have a very simple solution to the problem on the simulated distribution. So that's why we get a very simple post-processing KL. Let's generalize this idea to the constrained setting. And you realize that if we bring constraints into this problem, then suddenly it becomes challenging to keep the post-processing simple. So I will illustrate this using an example. We have two individuals, x1 and x2. We try to minimize the squared loss, and let's try to solve the post-processing problem, which means that we already have a predictor p, and we just try to do post-processing by solving this optimization problem on the simulated distribution dp. So let's suppose the marginal distribution of x is the uniform distribution, and the predictor p makes two predictions, p1 and p2, for the two individuals. And in this case, it's very, so by the definition of dp, we know that the conditional expectation of the outcome y given individual xi is equal to pi. So in this case, it's very easy to figure out what are the optimal actions. So they are, of course, given by the KL function. And in this case, it's the squared loss, which is a proper loss. So the KL function is just the identity function. The optimal action to take is just the predictions themselves. Let's try to add constraints to this problem. So we'll consider the simplest possible constraint you can possibly imagine, which says that there's a total budget of 1, which means that there is an average budget 1/2 per individual. And in this case, we can still figure out what is the optimal action to take. So it's given by projecting the point P1 and P2 to the feasible region, which is given by the bottom left triangle of the square. This corresponds to the constraint A1 plus A2 smaller than 1. So in this case, you realize that there's a problem, because now the optimal action to take for the first individual depends on the prediction of the second individual. And in general, it is very easy to come up with examples where the optimal action to take for one individual depends on the prediction of all the other individuals. So what this means that, first of all, in order to define omniprediction for constraint problems, we can no longer use the KL function. We need to consider much more powerful post-processings. But then this leads to the question of keeping post-processing simple. So how can we still keep post-processing simple when they are global? So we solve this problem by making some assumptions. So we assume that the population is partitioned into a small number of groups. You can think of these groups as demographic groups. And we assume that the optimization problems we're dealing with have this group structure. So this means that these functions f0 and fj, they don't directly depend on the individual x, but instead it depends on the group membership, g of x, of that individual. And this holds similarly for the constraints. So even with this group structure assumption, our problem is still much more general than the loss minimization problem considered in previous Omnipredictors work. The reason is that in previous work, the loss function L does not directly depend on the individual x at all, but here we at least allow it to depend on the group membership. And we also have constraints, of course, so that makes our problem more general. And also, many natural constraints are group constraints. They do naturally have this group structure. For example, for budget constraints, they are group constraints even if all the individuals belong to the same group. It's an overall budget constraint. But there are many interesting and famous group fairness constraints, such as statistical parity, equal opportunity, equalized odds. These are all group constraints. Cool. So this means that we are very happy with making this assumption. They still allow us to consider most of the interesting problems. Once we make this assumption, I will show you that now we are able to make the post-processing easy. So the post-processing still need to be global. That cannot be avoided just because of the example I just showed you. But here we can try to make it efficient to compute. The trick is to partition the individuals into blocks. So here we have 3 groups, so they form a partition of the population. And also we have a predictor, and by standard discretization, we can assume that the predictor outputs values 0, epsilon, 2 epsilon, and so on. And that gives us another partition of the population. And we take the intersection of these partitions to define the blocks. So each block consists of individuals that have the same G value and the same P value. And the observation here is that although the optimal action to take still needs to be global, they have to depend on the predictions of all the other individuals. They, however, does not need to depend on the identity of an individual in the specific block. The reason is that this optimization problem itself, because of this group structure, does not differentiate between 2 individuals in the same group. So there is no reason for the solution to depend on to differentiate 2 individuals in the same group. So what this means is that we can restrict our attention to this CGP class, which consists of functions that are constant on each block.
How complex can the group structure?
So here we assume that it's a partition of the population.
And that's one structure for constraint.
So it's a fixed partition for all the constraints and the object. So I just say that this is not exactly true. We need some, for example, convexity assumption so that we can apply Jensen's inequality in the right direction. Or we may need to randomize our actions, so either way. But those technical details are another point here. The point is that this group structure allows us to reduce the post-processing problem to a linear program or a convex program with a few number of variables. The number of variables is just corresponds to the number of blocks, and the number of blocks grows linearly with the number of groups. So if the number of groups is not too large, then we can efficiently solve the post-processing problem. So this is one small challenge that I want to mention, is that in order to solve the post-processing problem, we also need to know the probability that a random individual lies in each block. And in order to solve this problem, we notice that these probabilities do not depend on the actual optimization task we are trying to solve. So we can estimate these probabilities at training time and store these estimations together with the Omnipredictor to get an meta-Omnipredictor. And this leads to the view of Omnipredictors as data structures and not just predictors. I'm happy to chat more offline about this new viewpoint, but I don't have time to say very much in this talk. So now that we know the post-processings can be efficiently computed, we can meaningfully define Omnipredictors for constrained loss minimization. Suppose we have constrained task T, which is, of course, reviewed after we've already trained a predictor. And we want to solve this task T. So we want to compete with the best hypothesis that solves this task from a hypothesis class, capital C. So we use C benchmark to denote this hypothesis that we want to compete with. And since we already have a predictor, we don't want to solve this task from scratch. So we consider this post-processing task, which is defined on the simulated distribution dp. And we solve this task using a different hypothesis class C prime. And we are most interested in the case where we have group structure. So in this case, we choose C prime to be this class CGP, which is defined to consist of functions that are constant on each block. And I just mentioned this task TP can indeed be solved efficiently. And in particular, the complexity for solving this task is independent of the original hypothesis class, capital C. Now we say a predictor P is an omnipredictor if for every task T from a large family of tasks and its corresponding task TP, the model C post-process that we can indeed efficiently compute is a good solution to the original task T, which can be much harder to solve. In particular, this means that C post-process satisfies the constraints of the original task and then achieves a smaller or equal objective value than C benchmark. Of course, as usual, we need to take an error parameter into our definition, but the details are not very important here. Questions? So now that we've defined omniprediction for constraint problems, we show that we can indeed construct such omnipredictors. So we do that through this technical lemma, which gives a sufficient condition for omniprediction. I don't have time to describe the lemma in detail, but I will just say that the lemma allows us to reconstruct the results in previous work in a streamlined way, the previous omniprediction results. And not only that, this lemma allows us to construct omnipredictors in our constraint setting. And to state our result, we need to generalize the notions of multi-accuracy, multi-calibration to the group setting. So we define group multi-accuracy to be basically multi-accuracy condition on each group. And similarly for calibration and multi-calibration. And now we can state our main result. And I think you might already expect it. Our main result basically just says that if a predictor satisfies these group multi-accuracy or group multi-calibration conditions, then they are omnipredictors for constrained optimization problems if there is a fixed group partition G, for a fixed group partition G. The exact statement of this theorem is not very important since it's an informal statement anyways. And there are many other versions of this theorem in our paper. And I just say that basically our theorem subsumes previous Omnipredictor results in the sense that we now have constraints and we have multiple groups. And there are lots of versions. Some make more assumptions, some make fewer assumptions. And I just say that even the most restrictive setting supports many of the interesting loss functions and constraints that we like to think about. So finally, I would just briefly mention an interesting exploration that we did in this paper, which is motivated by the observation that fairness constraints alone do not prevent all harms. And in particular, we could be giving a fair amount of loan to each group, but we are not giving the loan to the people that are mostly likely to repay the loan from certain groups. And by doing this, we're causing harm to those groups because potentially we're making the economic situation for those groups worse and worse. So we ask this question of in what cases can we make sure that we give more loans to the people that are predicted more likely to repay the loan within each group. And indeed, we show that under some mild monotonicity assumptions, we can ensure this this property that we call rank preserving. And that is the end of my talk. Thank you.
Questions?
For your notions of multi-calibration, what is the learnability assumption?
So it's the same learnability assumption. Like if you have a agnostic kernel for C, then for example, we can just run the usual multi-calibration algorithm, but on the groups separately.
So the group structure doesn't make any difference.
Yeah. But yeah, at least here we're assuming that we only have a small number of groups.
Does it make sense to put this in an even more general context of just convex optimization or something like this? Like, could you define an omni-convex optimizer or something like this?
Yeah, good question. I need to think about it, but I feel that the problems we are considering are already pretty general. But we should check. Or if you have you currently have ideas on what are the more general forms of the problem.
Okay, thank you.